Welcome back for our last set of notes for chapter 12 here. We left off last time at osmotic pressure, but didn't really start to talk about it much. We use the symbol pi to denote osmotic pressure. You might remember from biology that osmosis is basically water moving across a semi-permeable membrane. So they say here it's the selective passage of solvent molecules, normally water, through a porous membrane from a dilute solution to a more concentrated one. So you could say water moves from a less salty area to a more salty area. And of course it could be salts, sugars, whatever, just a more concentrated is the direction it's going to move in. And so here's the example of a semi-permeable membrane in the middle of two tanks. And here it's more dilute, and here it's more concentrated. So water is going to move across the more concentrated side. Semi-permeable membrane, this gray thing in the middle here, allows the passage of your solvent, so in this case water, but blocks the passage of solute. So water can get through, but salt and sugars can't. So water naturally wants to do this, move from dilute to more concentrated. And osmotic pressure is the amount of pressure we would have to put on this side of this apparatus to stop osmosis from occurring. So we can calculate that. Here's the diagram of what's going on in this barrier. The semi-permeable membrane are these black lines. And here it shows that water can pass through, the small green is water, can pass through both directions, but the solute cannot pass through. And so that's the idea of semi-permeability. So osmotic pressure, or pi, is going to be moving from high pressure to a low pressure, the solvent to the solution from the last diagram that we showed there. Over time, it would look something more like this. And so we have the solution to this problem is pi equals mRT. That's the formula for osmotic pressure. So M is molarity, moles per liter. R is the universal gas constant. You'll remember that's 0.0821, moles atmospheres per liter Kelvin or something like that. It's got some long unit like that. Liter atmosphere per mole Kelvin is what it is. And then T is temperature in Kelvin. So Celsius plus 273.15 gets you to Kelvin. And so a lot of these units you've already used before, which is really nice. Makes it pretty easy to work with. So an application of this is a cell in a biological system. If it's a cell in an isotonic solution, you've got about the same solutes as you have inside. And so since there's not really a big concentration gradient of solutes from inside to outside, a little bit of water moves in, a little bit of water moves out, and you're pretty much the same size cell. That's where our body wants to be. Here's the red blood cell example. Kind of looks like that donut biconcave shape of your erythrocyte there. Now, hypotonic solution now, we've got a lot less solute in our environment and a lot more solute in our cell. And so water is going to want to move from less concentrated to more concentrated. So in a hypotonic solution, water is going to rush into that cell. It can cause that cell to really balloon out, or in some cases burst if the pressure is high enough. So this would be that same cell if we placed it in something like deionized water, perhaps, would give us a solution like that. And then hypertonic, if we've got a lot more solute outside the cell than inside the cell, it's really salty out here, then the water is going to move from more concentrated, or rather less concentrated solute to more concentrated, so it'll leave the cell and that cell will actually shrink. And here you can see that it's got some little appendages sticking out because we've lost so much volume that it's starting to collapse in, and so that's how we get a cell in a hypertonic solution. So let's look at colligative properties. We're focusing now on non-electrolyte solutions, so our solutes aren't able to conduct electricity in an aqueous solution. You might recall from Gen Chem that colligative properties are properties that really only depend on the number of solute particles in the solution. And if you haven't taken Gen Chem, then this might be a little bit new. But colligative properties are properties that depend only on the number of solute particles in the solution and not on the nature of the solute particles. So it doesn't matter if it's an ion or if it's a sugar or if it's a salt or if it's a big long molecule or whatever. As long as the number of particles is the same, it's going to behave pretty similar. And so one of the results of this is vapor pressure lowering. And so vapor pressure lowering is the higher the mole fraction we've done that a little earlier this year, of our solute, then the higher our vapor pressure. So our vapor pressure will become lower if we have a very small solute in a lot of solvent. Boiling point elevation, change in temperature for boiling point is equal to a constant, which is in your book, times molality. Little m is moles solute per kilogram solvent. So that is an important thing to note. And then freezing point depression, which is a change in temperature for freezing, is equal to, again, a Kf, which is a constant you can get out of your book. I think it's like 12.2 or some table like that, times a little m for molality, again, same as before. And these two you're actually going to see in your lab, so I'm kind of excited to see how that all shakes out. And then finally, osmotic pressure, which is another colligative property, pi equals mRT, which we've already talked about. And so all of these are colligative properties. They depend on the number of solid particles that we're going to have in a solution. So if we look at electrolytes, these can conduct electricity. So we have a 0.1 molal NaCl solution. So that's going to break apart. We're assuming it breaks apart totally evenly to 0.1 moles of Na plus and 0.1 moles per kilogram chloride ions. And so colligative properties, we said earlier, the same exact thing, depend upon the number. And so 0.1 molal solution is going to give us 0.2 moles ions in solution, because we're getting 0.1 moles of sodium, 0.1 moles of chlorine gives us 0.2, because sodium and chlorine break up, we're assuming, completely. And so this is where we get to calculate a Van't Hoff factor, which is lowercase I, and it's the actual numbers of particle in the solution after dissociation, so that would be like 0.2, divided by the number of formula units dissolved in the solution, and that would be our 0.1. And so basically it just tells us how many individual pieces will one formula unit break into. And different salts have different Van't Hoff factors, and so for non-electrolytes, I should be about 1, because if it doesn't conduct electricity, it's not going to break apart. So if it were sugar, it would be 1 mole of sugar divided by 1 mole of sugar, because sugar doesn't break apart, it'd be 1. For sodium chloride, it's going to be 2, because our number of particles in solution after they've dissociated is the 0.2. And then 0.1 is the formula unit, so 2 divided by 1 is 2. For calcium chloride, then, we'd say it's going to break into 1, 2, 3. So you would think it'd be like 3 divided by 1, and that's what it is. So colligative properties of electrolyte solutions. Boiling point elevation, we can calculate these really very similar to the way we did for non-electrolytes. The only difference is we have to multiply them by that Van't Hoff factor, because the number of solute particles it breaks into is going to have a pretty drastic effect on boiling point elevation, freezing point depression, that kind of stuff. It's the reason that we salt roads with mag salt and not table salt. Table salt, sodium chloride, would only give us 2 ions for every salt that breaks apart. But if we use mag salt, MgCl2, we get 3 ions for every salt that breaks apart. And so for the same number of pounds of salt you're putting on the road, you're going to get a lot more intense freezing point depression. And so that's kind of the logic behind those choices that we make. Osmotic pressure, again, same thing. We just throw the Van't Hoff factor in before molarity. And so hopefully that's not too terribly bad. Here gives you the example of mag salt that I was talking to you about, which should be 3. In reality, it's 2.7. There are small fluctuations in measured Van't Hoff factors compared to what they calculated should be. But if you look at them, we're pretty close. I mean, HCl should be 2, it's 1.9. Sodium chloride should be 2, it's 1.9. 3 is 2.7. That's not that bad. 3.4 to 4, we're a little off. 1.3 to 2, we're a little off, but not too bad. So a colloid. A colloid's a little different from a solution. It's a dispersion of particles throughout a dispersing medium. Basically, fog. Fog is a colloid. Milk, I think, is a colloid. Really soapy water is a colloid. These are suspended particles. And so colloid particles are big. They're large particles. Suspensions are not as homogeneous as they would be in a solution. And colloids typically exhibit a Tyndall effect. Basically, a Tyndall effect is a scattering of light when it hits these big particles. It's the reason that your headlights don't progress very far when you're driving through the fog. And it's the reason that on those goofy little spy shows, when they're breaking into whatever, they spray this little stuff in the room and you can see all the red lasers in the room because they're spraying a colloid, and that colloid kind of makes that light bounce out. And so a Tyndall effect, you take a laser pointer, shine it through soapy water, and you can see the laser the whole way through. And so here you have some colloid examples where the light, if it weren't a colloid, would just be light here, nothing else. But when it runs through the colloid, it starts to spread out. And here you have some sun rays kind of coming down through some fog in the forest, and it's kind of exhibiting the same effect. So here's some different types of colloids. Aerosols, foams like whipped cream, mayonnaise, jelly, I guess is a colloid. Why not? Fog, mist, smoke, that'd be the example of seeing a laser through some smoke. Certain alloys like steel are a colloid. Opal, like the birthstone rock thing, I guess is a colloid. So they're just all over the place for what can be a colloid. But hydrophilic and hydrophobic. You guys know this already, but hydrophilic is a water-loving molecule. Hydrophobic is water-fearing molecule. Those largely have to do with whether the molecule is polar or non-polar, as to whether or not it's going to get along real well with water. And so here you can see the colloid particle can kind of repel another colloid particle if they both are attracted to these negative charges. So that is an example of what that can do. And here's another example of what we can use these colloids for, because some soaps are colloids and kind of why they're good at what they do. So here's the kind of molecular design of soap, which is sodium stearate, and at the end you see you get nonpolar, 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 and then this double bonded O to sodium. So we get this polar end, and if it's polar, it's going to love water, so we call it the hydrophilic head. And nonpolar is going to fear water, we call it the hydrophobic tail down here. And so it's cool because with grease, we're trying to clear grease off a pan, and the grease is all nonpolar, and the water in the sink is all polar. If you just use water, the grease would never come off. But when you put soap into it, that hydrophilic head is going to bond with the water. Hydrophobic tail is going to bond with the grease, and that's the medium that allows us to remove those things in a watery solution. And so then here's the grease being kind of pulled apart by that soap, and that's the reason that works. Another cool example of colloids and really just bonding between polar and nonpolar is the idea of desalination. Trying to get the salt out of seawater. If you look here, there's a lot of salts in seawater. We got chlorine, sodium, sulfate, magnesium, calcium, potassium bicarbonate. You can't just take seawater and drink that stuff, because you look at just the sodium chloride, 19, 10, 29, looking at about 30 grams of salt in a kilogram of seawater. That's really, really salty. So there's a few different ways to desalinate water. Here's kind of a passive way of doing it. Wouldn't be very fast, but it'd probably get the job done. And basically you got sunlight coming down. Sunlight hits the seawater and heats it up. A little bit of water vapor leaves, but those heavier salts are left behind, and just the water vapor can leave. And so it's fresh water that condenses as droplets on that glass, runs down the window, and then forms drops into some sort of receptacle there. And so you can desalinate water, although slow, without a lot of energy input, really, just the sun. So that's kind of cool. Here's an example of reverse osmosis. You might have this in your house. A few houses in the area have reverse osmosis filters to get salts and ions out of the water. And basically the idea is this. We had learned that fresh water and seawater, or salty water or hard water or whatever, that water naturally wants to go from a less concentrated area to a more concentrated area. And we don't want it to do that. We want the fresh water, and we want to leave this stuff behind. So we take that hard water, that seawater, that whatever, and we put a pressure on it that is greater than the osmotic pressure. And we can actually force that water against osmosis to where it doesn't want to be, through a semi-permeable membrane that leaves the salts behind, pushes the water through, and we can get fresh water on this side. So it's just another way to accomplish the same thing. Here's an example of a kind of a cool little design. He's got this Survivor 35. I'm assuming he's in the ocean, and he's got one tube running down to seawater, and then it runs into this machine, and he's got this little pump. He pumps this piston, which shoves this water with a ton of pressure through a little filter inside, and the salts are left behind, and the fresh water is running out here to this beaker or this glass or whatever he has. So it's a handheld version of reverse osmosis machine. So kind of a cool example. And with that, I think we're done with chapter 12. So thank